Szumik.
Okay. Hello, everybody. I'm Max, and I would like to welcome all of you on technically first web3.krk meeting. And as I say, welcome in my name and whole software mention. Today we'll have 3 speakers with 3 different talks. And first speaker will be Tom Brand from Starkware. And he will briefly describe you what Starknet is and give you an introduction to scaling solution to Ethereum. So yeah, let's give him a voice.
Hello. What will be the other 2 topics?
Wait a second. We have some technical problems. Okay, you are here. You're online. Yeah, we hear you.
Okay. So hi everyone, and thanks for having me here. What will be the other 2 topics?
Other 2 topics will be Antoni from L2Bit speaking about layer 2 solutions. What is layer 2? And the third talk will be introduction to formal verification of blockchains. So, yeah.
Okay. So I hope we won't have interlapping talks because I'm also somewhat talking about LQs, but maybe it will be from different aspects. So yeah, let me share my screen and let me know if you see it. You see it?
Yeah, we see it.
Okay. Still.
Yeah.
Okay.
You're.
Yeah. So yeah, I'll be talking today. Or first of all, nice to meet you, everyone. I'm Tom, working at Starkware. We're developing together with a wide range of partners Starknet, and one of them is mention. I think we've been working together almost 2 years now. I'm not sure. And working together on building Starknet, on building all the tooling and the developer frameworks around it. So pleasure to meet you. I'll be talking about basically what's the idea or what's the main problems we see today in blockchains, what prevents them from fulfilling their potential or the promise, and how we want to help solve it in Starknet. Yeah, so a few words about myself. I'm Tom. I live in Israel, specifically in Nahalal. If you're familiar with it, this was supposed to be my, I don't know, job title, but I'm basically doing whatever Starknet needs. And you can follow me on Twitter. And before we dive into how we solve the problem, let's first understand what the problem is. Right? So first, let's start with blockchain. Blockchain started with Bitcoin in 2008 when Satoshi basically introduced Bitcoin with some implementation and some Bitcoin white paper to the world and started working since then. And then Ethereum in 2015 made another huge leap, basically generalized what Bitcoin did, which was a blockchain for a specific application for payments, to a much basically general computation, taking the same idea of what Bitcoin did and expanding it to general computation architecture. Now, blockchains are here for a while, but we don't see any really widespread adoption of it. And I think that the main or the first blocker to this is its slowness, right? So where does this come from? Why is this the case? And maybe one word before I go in. I assume you have some technical background, and I assume you have some blockchain background, but don't hesitate to just stop me and ask any questions. I don't have a lot of things to say here, and I think I have 30 minutes or 20 minutes. I don't know. But anyway, feel free. Okay? Okay, I hope. Okay, so in general today, when we want to talk about value, for example, about money, so when we want to expand it beyond, I don't know, agreeing on something with our friends, we want to expand it to a nation or maybe to a worldwide economy. Basically, what we do is we use some trusted parties, for example, banks or other institutions, and we basically delegate the accountability of the whole integrity of the system to those trusted entities, which are backed either by, I don't know, some well-known reputation or or a state. And if I want to transfer, I don't know, funds to Max, the way I do that today is through those institutions. I basically go to them and I ask them to transfer my funds to Max or to someone else. And usually it works. It's very fast. It's very convenient. But some may argue that this has downsides. I won't talk about why this is the case. I hope you also think that if you joined today. But blockchain basically, Bitcoin initially created a new way to solve this issue of how do I interact on value without having a centralized party to do that. And basically the way Bitcoin and any other blockchain that exists today offer to solve that is that you don't trust anyone, but you verify everything yourself, right? When I send a transaction to Max, the way that nobody else trusts nobody is just I propagate the transactions to everyone, as you can see it, and everyone execute those transactions, and then everyone knows that I transferred I don't know, those dollars to someone, right? Does this make sense? I mean, there are many other things about blockchains, but in a very high level, this is the main idea, and the construction with the proof of work or with block hash and stuff like that gave a way to implement this idea. Now, when you do that, you basically sacrifice two things, as we said. One is privacy, right? Because at least in the naive implementation of that, everyone sees all the transactions. So everyone specifically also knows how much money I own and what interactions I do. So that's the first thing that it sacrificed, and we won't talk about today. But the other thing that it sacrifices is scalability. And why is that? Because in order to allow anyone to participate in this network, the rate of transactions or the amount of computation that I require from each node is limited by the weakest link. So if I want to be able to participate without having a massive, I don't know, servers or farms or I don't know, just using my laptop, then it creates a limit on the amount of transactions that can be done in the network. And this is the main reason why we have scalability problems today. So for example, Bitcoin is, I don't know, 10 transactions per second, 20 transactions per second. Ethereum is a bit more, but it's nowhere near something that can satisfy worldwide need, right? And I think this is one of the main reasons why it doesn't do that today. Okay, any questions on that? Please say no. Okay. Great. So now I want to introduce some notion, and then we see how this idea or mathematical concept can help us solve the problem that we saw earlier. And validity proofs is a mathematical protocol which uses cryptography. And I'm not sure I'm the right person to describe it in a way that would blow your mind, but to me, this blew my mind in the same way that, I don't know, the first time I heard about public key and private key cryptography, it blew my mind that you can do something like that. So this is, to me, was the same kind of eureka moment. So what is that? Validity proofs are basically a way for, let's say, two parties, Alice and Bob, to interact in a way that if Alice executed a program I don't know, she computed, she went through a database and saw that my name is not included there, right? She executed the program. Then she can take this execution and prove it to me, Bob, that it is true without the need for me to re-execute it, right? So Alice can convince me, and I don't need to trust her. I just need to trust mathematics, that she searched through a specific database and my name is not there. And the only thing I need to do is to verify this proof. Sounds like magic. It is a bit magic, but it works. And basically, the nice thing about that is that we have computational integrity, meaning I don't trust anyone, and I know that the computation was done correctly, right? So how does that look like? And what's the nice thing about it? Let's say I have, in the context of what we said before, we have a lot of transactions, right? I don't know, 100K transactions that many people transfer the money between one another, right? So if before I had to re-execute all the transactions to know what's the amount of money that everyone has after that, now I can suddenly give those huge amount of transactions to an entity which is called the prover. The prover will execute the transactions and will generate a proof that the state after this execution, meaning how much money does everyone have, is true. And the only thing I need to do is to verify this proof to get convinced that this is the case, right? So is this clear in some way? Do I need to give another example? I think you're nodding your heads. Okay, sounds good. Now, the nice thing about this proof and why it allows us to scale is that the cost or the time it takes to verify this proof is exponentially smaller than the computation itself, right? And just to give a graphic estimation to what exponentially smaller means. So if, for example, this line is the amount of transactions that I want to execute, this line shows the amount of work that I need to do in order to verify them, right? So if it's very, very small, then the amount of work I need to do to verify them is approximately the same. But even though I increase the number of transactions in a linear way, the time it takes to verify the execution of those transactions starts to become almost constant. And this is the power of log, which again is a very nice concept. But what it allows us to do is that the sequencer or the prover can take the large amount of transactions, right? Do a large amount of work, but then propagate to the network only the proof itself. Okay, I will explain it in a minute. But okay, does that make sense? Or do you believe me? Okay. Sounds good. And a nice, even though it's not 100% accurate, a nice way of having like a mind model of what are validity proofs. So validity proofs to computation is something like what a zip is to a file size, right? It allows you to take a big file, compress it, while still having the integrity that this file is the same one that we had before. The compression here is, I don't know, linear, and here it's exponential, but this is a nice mind model. Any questions? There is a question? Yes. Live.
Hello, can you hear me?
Yes, hi.
Oh, perfect. You mentioned all that stuff about Merkle tree, am I right? And Merkle proof inside the Bitcoin.
I didn't mention Merkle tree and Merkle proof. We can, but
I mean, that's what you explained, that you got some Merkle tree and we validate only Merkle proof instead of execute all of transactions, as I understand you, right?
No, so we have a different kind of proof. A Merkle tree and a Merkle proof allow me to basically to take a set of items, right, and create a commitment to them with a Merkle tree. And then a Merkle proof allows me to verify the existence of a specific item in a commitment in a log amount of hashes compared to the size of the set. But validity proofs basically take this idea and expand it to any computation that you want, not just the inclusion of an item in a set.
Okay, yeah.
Right, so basically you can take any computation that you want, and maybe, actually I'm not talking about it, but you can take any computation that you want. I don't know, write a program, you want to prove that the 100 elements of a Fibonacci series that starts with 2 elements is something, right? Write this program and you can generate a proof to its validity.
Okay.
This is called validity proof. Specifically, as you can see on my shirt, we're using a system which is called Stark, which is an acronym for something, but this is a way to implement validity proofs. But the nice thing about them is that you can execute any program.
So in the end, it's based on conception based on Merkle tree, but it's not okay. Thank you.
It's not based on Merkle. It has many different mathematical algorithms. We can expand on that, but maybe let's see if we have time at the end.
Yeah, okay, deal.
Yeah, okay, good. Okay, so now we are at Act 3, and this is Starknet. And Starknet is basically how do you take this concept and implement it in a blockchain in a way that allows us to solve the previous dilemma that we have with regards to scalability, right? The dilemma that we have was, on one hand, we want anyone to be able to trustlessly verify what is the state. But on the other hand, this means that I cannot increase the amount of transactions because everyone have to re-execute them. So now let's solve it. Okay. So these are validity proofs. Starknet and ZK Sync are 2 examples for networks that implement it, right? But basically now we have 2 entities in the network. We have the big computers, right? Everyone sends transactions to them. They are the equivalent of miners, if you're familiar with this notion in Bitcoin, but let's call them the sequencers or the provers. And those entities basically get transactions, sequence them in some order, execute them, and generate a proof, right? And this proof, together with the block, is then sent to the networks of nodes of people who want to participate in the network and know what the state is. And now, instead of having to re-execute the full transactions that you have in each block, you only need to verify the small ZK Stark proof, the small validity proof. And you know that the block is valid and that the state that you have is really the state of applying this block. Does that make sense? Okay, and now we have this beauty that on one hand, we can have very big machines and execute a very high amount of throughput. And on the other hand, still allow anyone to run a client who participates in the network and verifies it. Nice. So in a very high level perspective, how does Starknet look like? So we have the sequencers, right, that validate and execute bundles of transactions and construct a block. Those are the sequencers. Then we have the provers, which takes those blocks and create a proof to their validity. And the nice thing about Starknet is that it's an L2 for Ethereum. And I won't steal the show for, I didn't get who is it from L2bit, but for L2bit, but on a very, very high level, this is all being verified on Ethereum. And so we inherited the security of Ethereum, which is, again, a very, anyway, it's very nice. And at the end, we have the full nodes, those clients that can just verify those proofs and knows what the state is. Okay. A few things about Starknet, or I'm now going back to just describe what we did in the past 2 months and what we had in mind. But when we went to build Starknet, we basically had there was always few options to choose from, and having in mind that we want to build an infrastructure that will serve, I don't know, decades ahead, things were built from first principles. So first of all, we're using Starks. As I said, there are other options for validity proofs. Maybe it doesn't say a lot, but Starks has no trusted setup. What is a trusted setup? Very briefly. For other proving systems, for example, Snarks, you need to have some ceremony in which some keys are being generated by multiple people. And basically, they are used to initialize the system. And then you have to ensure that everyone destroyed those keys and they're not using them, right? So it means that there is always a trust point in the beginning of the network. So Starks doesn't have that. It also is probably the fastest prover that exists. And I didn't discuss it, but generating the proof is a very, very heavy computation. So you need to be able to do it very fast. And it is also quantum resistant, meaning the only assumption that we're using is the existence of a hash function, which is a quantum resistant assumption. So it doesn't break under the existence of quantum computing. So this is the first choice that we did, going with Starks, not with Starks. The second choice that we did was to go with a specific VM that is tailored for proving, instead of going with the existing VMs that we had. For example, the EVM, the Ethereum virtual machine, that was tailored for Ethereum, not for proving. The main reason for that was that it allows us a much, much better performance, a few orders of magnitude. And the trade-off was, do we appeal for already an existing ecosystem of tooling and developers, or we choose that? And that was the choice. I think it paid off. And also it allows us to have much more flexibility when we design the network. So we're not, we live on Ethereum, but we're not, we don't have to implement every change that is done to Ethereum. So this is a bit on some choices that we did along the way. Yeah, so I reached the end, a summary of what we did. So Starknet, or generally validity rollups, basically gives you the same guarantees that blockchain gives you, but without the need to re-execute, right? And this allows the decoupling of who execute the transactions and who can participate and validate the network, right? At first stage, it's about scaling, right? We said we have two sacrifices in blockchains. One is that everyone can see every one transaction, and one is that we don't have scale. So we're first solving that. Next stage is privacy. And the nice thing about proofs, which we didn't discuss, is that they can also offer you privacy, but not today. And whenever we had the choice of what to do, we decided to build from first principles, and to look into the future and to the performance of the network. So that's what I had to say, and thank you very much again. I hope it was clear and not too high level and not too detailed. I would love to hear some questions, or in general, talk about anything that you want. I'm not sure if I'm out of time or not.
Somebody has any questions? It's probably a good time to ask them.
Any questions?
Okay.
Hey, yo, it's me again. It's not about Merkle tree. It's about Starknet. I'm wondering, so in the end, it's L1 solution for EVM, yeah?
Starknet is an L2.
L2. Okay.
Yes, it's built on top of Ethereum.
Uh-huh.
The source of truth is the state of Starknet contract on Ethereum. I didn't dive deeply into it. I just wanted to give the idea of how to use proofs to scale blockchains, but I can elaborate on that if needed. But what's
Yeah,
the question?
it's quite interesting for me because state it's I would say complex stuff on Ethereum. It can't sync it because it's global. And how you, as far as I understand, you doing some batches of changes, pack it and execute on Ethereum, or how it works in the end?
Okay, so let me go back to here. So what's being actually done on Ethereum is just the verification of the proof, right? So we have an L1 smart contract, so smart contracts on Ethereum are just, you can think of them as programs with state, right? So this L1 smart contract basically implemented the verifier, the Stark verifier. So if you give it a proof, it can verify it and output if it's true or false.
Oh, okay.
And then we create a Stark proof for a block, we send it to Ethereum, to this smart contract, and then it accepts it only if it's valid. And then when we want to update the state of Starknet, we're basically going to the Starknet core contract, and we tell it, please update the state from S1 to S2, right? And this Starknet core contract asks the verifier, did you see a valid proof to this state transition? And if the answer is yes, and there are other checks, but let's omit them for a second, then the state of Starknet progress forward.
Okay, okay, I see. So you compute only verifying on Ethereum, but all stuff is on your blockchain, right?
And to exactly.
Okay, okay. And you got some state?
Yes.
Is it global, same with Ethereum, or it's up to applications?
What's the question?
You got global state in Starknet?
The state that we have is, in a sense, very similar to the state of Ethereum, right? It's an address space where in each address you have a contract code with storage, right? The contracts are written in a language that can be proven. It's called Cairo. We didn't dive into it at all, but
Yeah,
Cairo
okay.
is basically a high-level language that we developed at Starkware. And the nice thing about it is that you can prove its execution, right? If you take, I don't know, a Rust program, you don't have the ability to just prove its execution. But Cairo, which is a very Rust-like language today, Max can tell.
It is.
Yeah, is you can compile it to an assembly that can be proven.
Oh, okay, okay. It's clear, your flow. Okay.
So the contracts are written in Cairo, but you have general computation, you have composability, you have all the good stuff that you have on Ethereum, just to scale it.
Okay. Okay, thank you.
Thanks for asking.
One more question.
Yeah. I'm here. No rush on my side.
Hey, thanks. Hi, I'm Josef. So my question is like, why don't you use Rust then? Like, why did you come up with your own language if it's so similar to Rust, as you said? And what other tech stack do you use?
Okay, great question. So in order to prove a statement, you need to be able to represent it in what's called an L, which is an algebraic intermediate representation, right? So it's a set of polynomials that you can then translate into a proof. And if you go back to the early days of Starkware, so when we wanted to create a proof to some statement, we handcrafted those polynomials for each computation that we wanted to have. For example, the first application that we did was a spot trading, right? So we created in polynomials, which, as you can imagine, is not a very trivial thing to do. The statements that are relevant for spot trading. I don't know. I verified the signature, I did the settlement, etc., etc. Okay. And then we understood that this is not scalable. I can't expect anyone to understand how to write things in polynomials, right? It's very equivalent to ASICs. If I want to compute something, I have to create a card for it. Okay. So then what we did was to say, okay, let's take a step backward, and what we'll do is we'll create a polynomials that describes the CPU. Right? I can basically define some opcodes, and then I can define some way that they can operate on some registries, and then I can feed it a program and prove its execution. Maybe it was too complex. Apologies, but my point is the following: Rust compiles to assembly, which can run on Metal, on CPU. But there's no way to prove it because it just doesn't go through anything that can be proven. So what we did is we created a specific assembly, which is called Cairo assembly. And this assembly is a specific, it can be proven because we built an L polynomials that describes the architecture of this CPU. Now you couldn't just describe a regular CPU because it is highly inefficient. It will be, the ability to generate proofs to those programs will be infeasible, right? So we created a VM architecture which is tailored to have very efficient proof, right? And then you can say, okay, so maybe write a compiler from Rust to this assembly, right? So it turns out it's not that simple because there are some inherent difference in the way things works. So originally we started with some very low level language, and then we tried to improve it. And then we realized that we just need a much better high level language, and we created it with a lot of influence from Rust, but with the changes that are needed in order to allow it to compile to our specific assembly. I hope it makes sense. But the short answer is because we can't. Okay.
Okay, one more question.
Yes.
Yeah.
Oh, okay.
What about the second part of my question? What are the tech stack do you use?
Sorry,
except for Cairo, what are other languages do you use? Is it the only one?
You're asking, do I have other languages which I can use to write smart contracts?
No. I'm asking if you use in Starknet other languages than Cairo.
Okay. Yeah, so Rust is used for everything but the smart contracts mainly. So the prover itself is written in C++. The sequencer was written in Python, but then it was very inefficient. So now it is being rewritten in Rust. I mean, there's endless amounts of tooling and stuff around Starknet. I assume this was not the question, but basically the stack is now being Rustified almost completely.
Nice, thanks.
I've got a question about the language.
What's your name? Apologies, I missed it, but I feel we're already...
My name is Yaroslav.
Yaroslav, hi.
Nice to meet you. We've got the same flow. We've got our own language in company. It's efficient to work with that blockchain as database. And we've got, I can say issue, but maybe it could be better. It's a people who work on company language. How you solve an issue with the people? You learn everyone from scratch. You hire strong developers and teach them, or how you work in Starknet?
You're asking how do we handle the challenge of teaching people Cairo?
Yes.
Yeah, this is one of the main challenges. I think one of the great benefits that we had is that right now is very influenced by Rust. So if you're coming from Rust, it is very natural to learn. I don't know if Marek is here.
He's here. He's waving.
So I think he can speak a lot about that. Marek was very influential in the design of and even implementation of the new version of Cairo. Really, initially, the meme of the community was that learning Cairo is hard, and this is, the ethos. If you were able to learn Cairo, then you are worthy, or something like that. But I think it was, it attracted some kind of people, but it didn't allow many to come. And now, when we made it very similar to Rust, and also just much better in general, then it lowered the barrier and allowed many more people to come. But in general, we focus on that a lot. We have a team of developer advocates, which is almost 10 now. And we also have, I would say, 10 more people in the community, which is not from Starkware, that are like ambassadors of this. And we have a lot of workshops, a lot of much longer programs that teach people Cairo and Starknet. But yeah, it is one of the biggest challenges that we had and still have.
I would add here that I'll explain my case if you don't mind. We've got some incubation program with the grants. For example, yeah, it's working really good. And when we came to some, I don't know, country with a good marketing, it creates for us a lot of people who learn our language. It's really good, Kima. Yeah, thank you.
Nice, thanks.
We have time for one more question if somebody has one.
I'm ready.
If anybody else wants to ask.
Nobody? Okay. It will be Tomek, like from our team. So he's here. You don't see him because he sits there.
I know how you look like.
Yeah. I was just about to say that you've seen me enough times. But I do have a question. You said about privacy and the proofs, that proofs could provide privacy, and I'm curious about that.
Okay, sure. So do you see my screen?
Yeah.
Okay. So I won't find another presentation. I will speak and you will believe me. So one of the other nice, so we said we have a nice property of those proofs that they are exponentially smaller to verify, right? But another thing that you can, and this is where the term ZK, which means zero knowledge, you can also generate those proofs in a way that leaks zero information about the computation itself apart from the statement. I'll give you an example. Let's say that I'm trying to prove to you that your name does not exist in the database. So I can construct the proof in such a way that, now there's feedback, that you will learn nothing about the database itself apart from the fact that you do not appear there, right? Or to give another example, I can generate not only the proof, there needs to be some changes to the blockchain, but I can generate the proof in such a way that you will only know that the state has moved from S1 to S2, but you will learn nothing about the transactions that were executed. Right? Does that make sense? If you're asking what's the technical way of doing that, then it's a bit more complicated, and then we need to talk about how do we generate those proofs. But this is also a property that you can have, right? They don't only give you validity, but they can also give you a zero knowledge about the computation itself. And for example, Zcash, if you're familiar with it, is a blockchain that uses validity proofs in order to create a private payment network where you have transactions that are being propagated, but the transactions leak no information on who's the sender, who's the receiver, and what's the amount. And so you basically don't know what happens there apart from the fact that it is valid, which is, again, mind-blowing, at least for me. Does that answer the question?
Yes. Yes, it does.
We'll reach there as well. So Stay tuned.
Okay, so thank you, Tom, for your presentation. And
Next time I will come visit you.
yeah, it was very nice. And right now, after we got an introduction to one specific layer 2 solution, we can hear from Antoni from L2Bit, which will speak about layer 2 more generally and give a probably overview of the whole what it is thing. So I'm giving him a voice.
Okay, thanks. Can you hear me? Yeah. So yeah, as you said, my name is Antoni. I'm a developer at L2Bit, and I like to talk about layer 2s from time to time. So yeah, normally I start my presentation about asking people.
There is no slides?
Yeah, okay, so maybe slides, yeah. Normally, I start my presentation asking people how much of you has even heard about layer 2s, but, you know, Tom really did a good job about telling you a bit more, but maybe let's imagine that you were not on this meetup before, and how many of you have ever heard the term layer 2? Raise your hand. So, yeah, probably most of the people. Okay, so for those who knew and those who didn't, my presentation will be like this. First, we start with the problem, so why layer 2s were created. Later, we talk a bit about the solution from the bird's eye view, let's say. And later, we'll discuss the details about layer 2s, about risk associated with them. And also, I will introduce what L2Bit is. So, to start my presentation, very important remark at the beginning. It will all be from the perspective of Ethereum. So, you know, there are multiple ecosystems, and maybe layer 2s are different on the different ones. But I just specify the Ethereum one. And mostly, I cannot even talk about different ecosystems. So, yeah, this will be from the perspective of the Ethereum. So, for the sake of this presentation, let's just focus on Ethereum. Okay, so there is this triangle that everyone in crypto are crazy about. So this is the blockchain trilemma, which basically says that you cannot have three of them. And for Ethereum, it is safe to say that we are focusing on security and decentralization. What does it mean? It means that Ethereum is decentralized. It's a bit slow, yeah? Can you hear me? Okay. So it's a bit slow, but what are the advantages? It can run on every PC, so there are low hardware requirements. It allows for the geographical distribution, so even with poor latency, nodes can reach the consensus. Also allows the fast computation and propagation of the block, which basically allows us to reach the consensus very efficiently. Also, it tries to be secure. At the same time, it's a bit expensive, but nodes have to be compensated for the computation, and also this mechanism prevents spam attacks on the network or creating infinite loops on the runtime. So yeah, those small red pills I have shown to you, like there are very, very big green pictures, but also very small red one. So we have low throughput, and it is expensive. And when we look at the top of this triangle, the scalability one, it becomes a bit of a problem. Because what does low throughput mean? We have approximately 12 transactions per second on Ethereum. So if every human being on Earth would like to make a transaction on Ethereum, it will take us 20 years. So basically, for the scalability part, it's a really big problem. Also, it is expensive. You know, imagine just trying to buy a bread with Ethereum, and basically the cost of transaction can be more than the value. And it is mostly determined by the gas price, which can be, you know, which can be way higher when there is, let's say, meme coin mania. So what, maybe we should not buy bread when there is meme coin mania. I don't know. This network should not work like this, right? Okay, so yeah, we see the problem, right? So let's fix Ethereum. What can possibly go wrong? First idea that everyone has. So let's just increase the block space. We'll fit more transactions in the block. But it will take us more time to process this transaction. It will be harder to reach the consensus. Also, the state will grow in size. It will be a big centralization force. So the great thing that we have, this green decentralization, will be at risk. And that is why Ethereum does not try to expand the blocks to the bigger one, because it wants to keep the decentralization. Okay, so that's the first idea. The second is maybe make transactions cheaper, right? So everyone is complaining why my ETH transfer costs like $5. Maybe we should make it like 5 cents. But if we reduce the cost of the transaction, it could become a like DDoS attack vector, or there can be a spam attack on certain contract. So let's say this security, especially the economical security, will be at risk. So that's the first hard to swallow pill. So Ethereum cannot scale, right? It is really hard to swallow, but trust me, it will become better. So yeah, Ethereum is sick, we cannot heal it. So maybe let's just build another blockchain, right? So what can possibly go wrong? So there is this public blockchain paradox as I call it. So the main idea, it is very hard to bootstrap a public blockchain. So it is very hard to start the network similar to Ethereum with the decentralization and security properties of it. And that is because, for example, if you would like to right now start the proof of work network, a miners from one can switch to your network and perform a 51 attack. Or in case of proof of stake, it will take someone very little capital to just outvote the majority and change something for the bad. But you know, people have tried, right? Everyone is trying to bootstrap its own L1. And what can possibly go wrong? So first case, it's Polygon, that you are not open to everyone, you are just open to a certain amount of people, but it is not that decentralized, right? So only few people decide what will happen with the network, and it is not yet sure who holds the keys. It can become a really, really big mess, and I don't think whether we want blockchains to go in this direction. The second case is you can create a blockchain which is super, super fast, but it will have like a very high hardware requirement. So you have to run it on the like servers, like with petabytes of RAM or whatever, and it can lose the consensus from time to time, and the outage can like stop the network from functioning. So the second hard to swallow pill is Ethereum is here to stay. I need to drink. Okay, it is really hard to swallow pill because you cannot fix Ethereum, but it is here to stay. So what should we do, right? Maybe we should just use Ethereum. It has low throughput, but it is decentralized. It is expensive, but it's secure, right? So maybe let's make Ethereum great again. Okay, we'll introduce the scalability. We'll do it. We can do it. No. It's hard to swallow, but we cannot solve the scalability of Ethereum on its own. We'll try to build another blockchain, but this time we'll connect it with Ethereum. And that is basically the idea of layer 2. So you move some operations off the chain, but you inherit the properties of Ethereum. So everything that was green before, you've seen the decentralization, the security, it still in theory becomes green, but also you are gaining the scalability. And in a very, very basic example, you can see that the cooperation is like this. Layer 1 needs layer 2, and layer 2 also needs layer 1. So it became, there were a few ideas in the beginning. The first one is Lightning Network. In the beginning, it was on Bitcoin. Later, the company Raiden Network tried to deploy it on Ethereum. But obviously, you probably never heard about this one, so it never really panned out. Also, there was an idea about the Plasma and OMG network, but basically it's not working anymore, and I don't think they are even developing this project anymore. Okay, so then came a time that someone came up with a great idea for layer 2s. And the thing that we currently call layer 2 is a rollup. So you can think of a rollup as a blockchain that posts their blocks to another blockchain and inherit the consensus and data availability of that blockchain. So this consensus and data availability is the green things, the green properties that we really want. That's why we are using Ethereum. But you know, everyone wants to use Ethereum, but it's too expensive. So that is why the main idea is just to move to layer 2s. And in the very, very easy mental model, you can think about is that layer 2 is just packing multiple blocks of layer 2 into one layer 1 block. But it's just a really high overview. But stay with me, we'll get more into the details. Okay, so you take a lot of blocks, you put it into L1. So you can fit more in the one L1 block space, but at the same time you preserve those properties of Ethereum. Another mental model, so you can think about a blockchain of like a train. So without those balloons are layer 2s, you'll have those very heavy elements in this wagon. But with balloons, you can basically fit heavier ones into the train. That is also another way if you want to grasp it. But after we have this very basic image of what layer 2 is, so that we are packing something or we make something lighter so we can like feel more, let's go more into the details. So I created the visual guide for how to roll it up. And basically, what this roll-up even is, because for me in the beginning it was not really clear. I would say that roll-up system consists of two things. The first part is Ethereum, and there is a smart contract that is deployed on Ethereum, and it stores the state of the rollup. And the other part is a rollup itself. So here are the nodes, they are running the software, very often very similar to the Ethereum one, but they are listening to the Ethereum, what's happening there on the bridge contract or any other contract that they specify, and they, from time to time, post the transaction here to update the state. And here you can see that there are balances, their state is oversimplification. So let's imagine you are an Ethereum maxi, right? And you want to use this rollup because you really love Ethereum. You want to use it, but it's too expensive. So you decide to use this new super good rollup. You go to the L1 bridge, you deposit your money, and this bridge emits an event which nodes on layer 2 listen, and later they update their own state on layer 2. It is a very big oversimplification, but I want you to just understand that it's not like they are super connected, but they are like layer 2 is listening to layer 1 at some point. Okay, and later what's happening is now Maxi is operating on layer 2, so he can do like DeFi magic, double his money, triple his money. He can spend a lot of gas, but this gas will be cheaper than doing it on layer 1. And what rollup does, it's from time to time, it just updates the state on layer 1. So you see that Maxi now has 100 here and 100 here. And going more into the details, what this rollup even stores is that it posts the blocks, so the input data, and also new state root after the computation. So we can think about it that layer 2 is just moving computation off the chain, and you just post the data. And withdraw is, as you can probably think of, very similar, that you just say that you want to withdraw, and the rollup is also updating the state. Like, this is very big oversimplification, like most of the rollups don't work this way, but it's just a very important mental model, just to grasp it in the beginning. And as we can see, Maxi was able to deposit 1 Ether, make a lot of transactions on layer 2, which were way cheaper, and later withdraw this money. So for him, it was good to interact with the rollup because it was way cheaper. And at the same time, he was still as secure as using Ethereum, at least in theory, if the system was implemented correctly. So probably that's the scalability that we want, right? We can use something that feels like Ethereum, that works like Ethereum, but it's cheaper and more scalable. And even more detailed explanation for those of you who are like the most interested about layer 2s, in the plain words, in plain English, It's just you give inputs to someone else and you let them perform the computation of the chain. Okay, so you do the computations of the chain and you store those inputs on the data availability. In many cases, just you store them on Ethereum. Later, you make someone else to prove that the computation was correct. So after he posts this L2 state root, you have to make him prove that the computation on the inputs were correct. And we'll get to the point of the proving, but for now, let's just assume that you have to prove that the computations were correct. So you just store the inputs, and later you make someone to prove the computations. So we ensure their validity. And at the end, the idea is to ensure that verifying the proof is cheaper than verifying the original computation. So your rollup should be economically sustainable. And that is what really brings scalability to Ethereum. What makes rollup scale is that this simple equation is like DA cost, so like posting inputs plus proving proving cost is smaller than just the original computation. So you can make a lot of transaction on the rollup, but still inherit the properties of Ethereum. So basically, cost of this one and cost of this one has to be like smaller than if you just interact with Ethereum here. Okay, and the summary at the end, let me grab a water. It's that a rollup posts their block on another blockchain, okay, inherit the consensus and DA from that blockchain, have a special contract that maintains the state root, and it should be trustless, permissionless, and censorship resistant. So what does it mean? It means that everyone can run their L2 node and everyone can post the state, and if the state is not correct, we can make a dispute, or you cannot even post the incorrect state. But you will soon learn that it is not always the case, and not all the layer 2s currently are working this way. And the very, very basic idea is that it provides the base layer user, that someone that really likes Ethereum, that wants to use some technology like this, with the cheaper transactions, but it still preserves the properties of Ethereum, and it grows the Ethereum ecosystem anyway. Yeah. Even this random user of Twitter called Vitalik Buterin, he even wrote a blog post that there is a rollup-centric Ethereum roadmap, and that is the way the Ethereum thinks to scale. So even Ethereum Foundation is really propping this up. And what is really interesting, in my opinion, is that Ethereum has a market approach to rollups. So basically, there is no official Ethereum rollup. So for example, they can create it like EIP rollup and create just a official Ethereum rollup that we should all use. Instead, many companies compete to create the best solution. And it is also very interesting that currently we are living in such a times that it's even feasible to run such a rollup, because you have to have the certain user base to make it feasible to post the state and everything, because there are some fixed costs that, for example, if only 3 people try to run the rollup, it won't be feasible. You have to have a lot of user base to just run the rollup. So that's a very interesting time to be in. But this is an open market in early stages. So you have to remember that the technology is still in its infancy. There are bugs, there are hacks, and whatever you name it. Only bad things. And nothing prevents bad actors from entering. So basically, anyone can create a rollup. Anyone can try to scam you into depositing your money on layer 1 contract. So users are exposed to a lot of risks. And that is where L2Bit is coming. L2Bit is a research and analytics webpage where we just have all the projects currently deployed on layer 1 on Ethereum. We present some statistics about them, so maybe total value locked, how much is basically to hack for the hacker, or how much is locked for the DeFi. The activity, so how many transactions are happening, and what is interesting is that for almost half a year now, there is more activity on layer 2s than on on Ethereum, so I think it's appreciating slowly, but it's getting there. But what I think is the most interesting about L2Bit is the risk analysis. So basically, we looked at every rollup, and we came up with this, let's say, risk matrix to say about the risk of every rollup. And basically, you can see what it means to use Arbitrum, what it means to use OP mainnet, what are the risks that you are, as a user, exposed to, and what you have to have in mind if you store there a lot of money. And yeah, and after that, I will try to go through every of this column and just try to slowly get you into our risk framework. So maybe you will see some, let's say, correlations with what I talked about before, right now. So the first idea is the state validation, right? You remember this L1 contract that you have to prove the computation were correct. So it happens that there are two ways of doing it. There are optimistic rollups, and there are zero-knowledge rollups. Maybe we'll not get into many details, but the very brief example is that in optimistic rollup, you just optimistically assume that everyone is telling the truth, and only someone can go to the judge, and the judge, so the layer 1 contract, will state whether this new state update was correct or not. But in the case of zero knowledge, as you can see now, Ethereum is like verifying ZK proof. So it means that you cannot even post the new state root, which is incorrect. But it's way more complex. Excuse me, we'll not get into more details because I think it's really hard to talk about it from the best principles. But here you can see the L2-bit, part of the L2-bit. So basically you can see that we assume that some projects have, maybe let's start with the black one. So there is a ZK proof. So everything is, let's say, almost safe. That there is a contract that is making the state correct on layer 1, but some systems just have it in development. So if you are using, let's say, Optimism, you cannot even be sure that the new state update was correct. And this is something you as a user have to be aware of. The second one is data availability. So I've shown you that we have to post the blocks on layer 1, and it happens that it is a rollup. But there are some scalability solutions called Validium, which do not post it. They just post it to the server, the third-party server, and it is called Data Availability Committee. So basically, few servers have to sign that they have the data, but what basically means is that this data is somewhere else, and you have to trust someone that is there. And it's really not good for us. It's a yellow one. We stated, like, basically you can think about it. What will happen if your rollup will shut down? If your rollup will shut down, in the case of on-chain data, you can reconstruct it from the Ethereum state. But in the case of Data Availability Committee, you have to ask Data Availability Committee for the data. And that is a thing that you should consider when using such a rollup. Also, there is a risk called upgradability. So can L1 smart contract be upgraded? And it is currently a big, let's say, a big issue, because at one point we want to have immutable contracts. So we don't want to upgrade them. We want to have this immutability of Ethereum. But just look at this picture. It's this picture of Arbitrum. And it has a lot of contracts. And to be honest, deploying it and making sure it works, it's really hard. And even if one of these contract is malfunctioning, you have to probably redeploy everything. So what happens in most cases is that there is a delay on which you can update your contract. So the user, if he is not good with the upgrade, he can just move away from the rollup. But some contracts are just instantly upgradable. So it means if you have the money on layer 1 contract, someone can just press the button and drain all your funds. And it's really important to know that if you store extensive amounts of money on any of those contracts. So remember the website and check the risk there. Also, there is a sequencer and proposer. So I have lied to you a bit that we just do it in the one step, but what most rollups do is that they have two roles. One role is responsible for just posting the blocks, and the other one is responsible for posting the new state route. And basically what it means is that there is a sequencer who orders the transaction and posts them to L1. So you have to talk to the sequencer, and he will decide which transaction in which order will happen. And that is exactly what we show here. So here you have to think about what will happen if the sequencer will go down. So your rollup totally shuts down. You have your 100 if there, and what can you do? In the case of force via L1, you can just call the L1 smart contract and withdraw your money from the bridge. But in many cases, there is just no mechanism. So if the team shuts down, or I don't know, whatever happens, you cannot withdraw your money. So that is also a very important risk to know about. And the last one is a proposer, so someone who updates the state. And it's, let's say, very similar to the proposer one. So you have to also think about what will happen if he just goes down and he's not responding. So in many cases, you just cannot withdraw your money, so you cannot update the state. You earned 100 there, but he will not update your state. You cannot withdraw. But in some cases, you can just use escape hatch, and you can self-propose the new state, so you can post it. And that is the main idea. We also create this small handy risk rosette that just gives you all the risks in one place, so you can quickly gather and take a look what are the differences between certain projects. So I think it comes quite in handy. You can also find it, maybe not here, but also on our website you can find it in the main page. And that's basically it. That's the idea. So you have layer 2s. They are scaling. They are trying to scale Ethereum. They are trying to still have those properties of Ethereum, but at the same time, you see there are a lot of risks, and that is why I think every user, before just trying to use one of the systems, should just know the risks, that sometimes your money is really at risk if something goes wrong. So that is basically it. Maybe any questions regarding the topic? Yeah.
Yeah, do you hear me? Yeah. So first of all, my name is Vladimir. Thank you very much for presentation. It's really nice, and L2Bit resource is also looking absolutely great. It's really useful thing. I have a couple of questions. The main one I think is caused with the point that I have not following the Ethereum infrastructure updates for some time, maybe for a year or 1.5. And the first question I see that, like, when we talk about scaling solutions, is what has happened to Ethereum 2.0. That was like there was a lot of talks about that there should be a solution for scaling, and it is not clear for me. Actually, do we talk now about Ethereum 2.0, or it is still good old first version of Ethereum?
So you mean whether the 2.0 introduced the scalability, right?
Yeah, because a lot of discussions was before mainnet of Ethereum 2.0 was launched. I guess it was maybe a year ago about solutions to scale.
Yeah, but mostly Ethereum 2.0 was just the upgrade of the consensus mechanism, and it did not introduce any scalability. Let's say there were a lot of misconceptions about this one, but literally after the update, the fees stayed the same mostly, and the throughput is almost the same. So basically, the problems still exist about this one, and rollups are still needed.
So does it mean that this problem exists for both versions of Ethereum?
Yeah.
Both first, yeah, got it. Thank you. And if it's okay, I would like to ask one more question. Like, again, from me as a person who is not really deeply into the context of like in technical details how current ecosystem of blockchain works, like it looks to me that if we have some kind of another blockchain as a layer 2 solution that could perform some transactions and prove that it was done correctly, then two questions coming out from this idea. The first one is that why do we need Ethereum at all? Like, we have already blockchain that can perform transactions and prove that they are valid. What else do we need? And the second one, what allows layer 2 solutions to perform transactions that cheap, much cheaper than Ethereum? So I guess two questions should be somehow related, and I guess that I missed something.
So just to sum up in the beginning, your first question was why Ethereum at all? Why should use it Ethereum, right?
Yeah. Why do we need Ethereum if we looks like has something?
So the basic idea and the thing I wanted to talk in the beginning is that is just everything from the perspective of Ethereum. So there is a certain network of Ethereum. People believe in it. People use it. People like those properties, and they want to use it, but it's not scalable. So that's why the L2 solutions are created. But basically, nothing prevents people from just creating another layer 1 and use it. It's just this network effect of Ethereum, and that people want to stay on Ethereum on something similar to Ethereum. And that's the idea of the rollups.
But if you take some layer 2 solution and use it just by its own without Ethereum, like just believing
it's possible.
Proofs, so it should work, right?
Yeah, it's all just to the users.
Okay, thank you.
Can I add something? So the idea here is that these networks are basically, so those blockchains, the sequencer is just one computer, right? So if we used it on its own, it wouldn't inherit any of the security and any of the security properties of Ethereum, right? It's only safe because it inherits them, right? It doesn't have them on its own, right? So right now the rollup-centric Ethereum roadmap says that people will not use L1 to transact, to do things on L1, right? That user-focused networks will be L2s, but the L1 basically provides the data availability. So we know the data availability, and if something goes wrong with an L2, we can use L1 because we are sure that if we transact on L1, the sequencer will not censor us, or we can, for example, we can just withdraw to L1 if something goes bad, right? So basically, those L2 networks work like a charm only because Ethereum is under them.
Yeah.
It looks like if we trust, if we say that we trust to proof of layer 2 blockchain, we trust it, but not as much as Ethereum, and this is the main difference. Is it correct?
Yeah, and also there's also a very important factor that we have to take into account, that is putting it into Solana, you're not putting it into Polygon, you're still having it on Ethereum. It is super safe on this risk minimized bridge, in theory, okay? And you are using the layer 2. So I think currently the biggest selling point of layer 2s is just those risk minimized bridges, that you can just bridge your value to other layer 2, use it as this guy, this Maxi was using it, but you are still having it on layer 1. And that is basically the most basic idea about layer 2s, that you have a place where your money is safe and you can use the other network, but if this network shuts down, you can always exit safely and your funds are stored, right?
Yeah, thank you. And also, does it make sense that the point is that transactions are cheap is reached because like there is smaller amount of value locked in these layer 2 solutions? So this is it the main reason why transactions are much cheaper?
No, it's just they are different networks than Ethereum. So there is less nodes, but basically it's just you have other environment that everything is running. So they can set the transaction fees to be smaller, let's say. Maybe Adrian can elaborate.
Yeah, thanks. Yeah, hi, I'm Adrian from same team, so we can also. So the transactions are cheaper because the computation, the really expensive part that is really the expensive part on Ethereum, right? Because every single node to reach consensus need to perform these operations. You send one transaction on Uniswap or somewhere, and every single node, every validator needs to execute it. That's why it's expensive. And we move the execution out from Ethereum, which means that Ethereum nodes don't really execute these transactions. And maybe a single node on L2, like this sequencer, executes it, or for example in Starknet it's the prover, but there can be just one computer that executes it. That's why it's cheap, right? It's really cheap to do this in one place. So we move the execution of Ethereum, and we only prove to Ethereum that we did the execution in one of the two ways, right? So that's why it can be much cheaper. And to go back to the question that Michał already replied to, is that the consensus, right? Reaching consensus is one of the most difficult things, right? The Bitcoin came up as a new thing because they figured out how to have a consensus, distributed consensus of who has how much money, because everything else pretty much was done, right? But how do you reach consensus in distributed manner is extremely expensive and extremely difficult. And rollups don't have any consensus. They only actually have consensus because once they have something, then they put it on Ethereum, and the one that Ethereum decides is the one, then it is that then this is the valid one, right? So rollups cannot exist without Ethereum, right? They cannot just say, okay, let's ditch Ethereum and we can work, because there's no consensus to be reached without Ethereum. So that's another point. And going back to your very initial question about Ethereum 2.0, because I was actually following this as well. So there were ideas, right, that Vitalik and the Ethereum Foundation had at the beginning, that there would be some data sharding and like multiple shards. They wanted to do the quadratic sharding for the data and for computation. So there was idea that some parts of the network do some smart contracts and some parts of the network do execute others, etc. There was this whole idea. But once they realized that the rollups are the way to go, the idea of Ethereum 2.0 has been ditched. There's no idea of Ethereum 2.0. It will never happen, ever, right? That's the current approach. They actually changed the consensus, which was called a merge, because it was first called Ethereum 2.0 as like the smallest part without any data sharding. It was called the merge actually to switch from proof of work to proof of stake, which is the consensus mechanism. And well, not exactly, but yeah, more or less. So now the approach is that Ethereum will stay as it is. It will try to add some additional features to make rollups cheaper still, right? For example, now there is something called proto-dunk sharding, which, so actually that's a bit different, which means that there will be a dedicated place in the blocks of Ethereum coming, which is a temporary storage for data, which means that rollups, rather than put the data onto Ethereum, they can put into this temporary space on the blocks, which is much cheaper because it's only temporary, just for the time being, so that everyone can verify that the rollup was fine. But the whole idea is that Ethereum will stay as it is with small additions, which will make L2s and rollups scale it outside, right? So that's my understanding.
Yeah, to sum up, the very basic idea is that on Ethereum, just see the inputs. So let's say 2 + 2, and later you just post 4 to Ethereum. And every computation, this computation was really simple, but imagine that you have to read few storage slots, that you have to write something to storage slot. It costs a lot of gas. And basically all of that is happening somewhere other else, and just output is stored here. And that is why it scales. Thanks.
Okay. Sorry. One more question.
I just opened L2 and saw that you not mention about stage of maturity of product.
Yeah, it's
or
our
I miss it.
It's our fairly recent feature that we've added, and it focuses on the, let's say, stage of the development, because you remember that I've told you that not many systems currently are working as they should be, right? So in the perfect world, it will just be all permissionless, open to anyone, without the upgrades. But you know, there are some systems that are more developed than the other. Some are more safe than the others. And just this idea of a stage is like, let's say, we just show how far away are they on the roadmap to scaling in the, let's say, Ethereum way. It is not about security at all. It's just about this roadmap that we want to decentralize, that we want to have it economically secure, but not about, you know, hacks or whatever. We are just doing the work on, let's say, a roadmap for every rollup.
And do you mean a roadmap of a product or roadmap that you saw in
if
your
you
team?
if you go to our website, there are requirements for this one, and we have like requirement for every stage to be passed. So, for example, if you want, you have to expand the stage button, and
Oh, I
Yeah.
see. Okay, thank you.
and you see all the requirements. So, so for example, stage 1 rollup can be upgraded immediately. Let's say you can your money can be stolen, but the stage 2 rollup has a very long delay, so it means that it's more secure. And that is our basic idea, that stage 2 rollup is more of a rollup than stage 0.
Okay, thank you.
You're welcome.
Is there any questions? Okay.
So hi, my name is Michał Posłuszny, and one question came up to my mind regarding the gas fee. So we already know that this is cheaper because we only need to validate proof and not do the whole computation. But is there a chance that the L2 layer gas fees will get higher and higher, and we will need to do something like layer 3?
Yeah, it's an open question really, and no one really knows the answer. But basically, if we just create layer 2 that is very similar to layer 1, so a lot of nodes have to redo this computation from layer 1, basically we could end up with the same thing. So I think right now the idea is that there will be many rollups, and it will just span across the ecosystem. But basically, if we just want to create one rollup for Ethereum, it will be very hard. Or maybe Adrian can elaborate.
Okay, and does this Stark system, which provides single node for computation, could improve the situation or change it somehow?
Can you repeat the question? Like, you mean there is one node?
Yes, like it was mentioned on the previous presentation that there is the one that focus on computing the proof.
Yeah. So you mean that you can make the proof and verifying is way cheaper, right? So you can spread this fixed cost on many more.
Yeah.
So currently the idea is that ZK rollups will scale more because this fixed cost, if there is certain amount of users, it scales better. But to be honest, it will be determined in the future. It is hard to right now say which will scale more. But answering your first question is that, yeah, L2 can still become really expensive if a lot of people start using it.
Yeah, thank you.
There is no magic included.
Yeah, actually, there's one interesting thing when you think about this kind of layer 2s is that the more users they have, the cheaper the gas becomes. And this is because the layer 2 pays the gas cost to put stuff on Ethereum. And the stuff that they put in Ethereum is very small compared to the whole computation that happened on L2. But if you have just one person doing stuff on L2, that one person will have to cover in the cost of transactions the whole cost of putting on Ethereum. But if you have 10 people, the cost of putting on Ethereum kind of spreads into these 10 people, and it actually goes down for a long time until it reaches some other extremes. Like, for example, actually the amount of data is so big that it doesn't fit in a block on Ethereum, and then suddenly you reach some other limits. So in theory, yes, you're right, the gas cost will ultimately begin to rise once you get some other limits. But the nice thing is that at the beginning, the more users you have, the cheaper the gas becomes. So yeah, it becomes much more complex if you look further into it.
Okay. Okay, so we have time for one last question here. So, please.
Okay, my name is Bartek, and I've got a question. As far as I'm concerned, an alternative to rollups are parachains. Yes?
What do you mean exactly by parachain?
Parachains, like, for example, Kusama or Polkadot, overall alternative to rollups to solve scalability problem.
I'm not really into, but you can ask the question.
Okay, so it might not be a valid question, because I wanted to ask if rollups actually has advantages over parachains, considering that you talked about scam risks.
That's a really hard question, because probably the idea of Polkadot is that you can somehow connect Ethereum to it, right?
Yeah, I guess.
So if they are able to pull it off, but to be honest, I'm not really an expert on that one and have never thought about it. Maybe Adrian?
Yeah, I would say that there is a major advantage, in my opinion, meaning that a well-constructed rollup, which if you look at L2-bit page, there are only 2 right now, which are not even have valid computation. So most of them don't meet this, but we know how to do it, it's just complex, is that if anyone on L2, for example, let's say you put your money on Arbitrum or Optimism once they reach the final stage. If you put the money there and then they all get arrested, everything is closed down, they burn down their servers, everything happens, you can still, by interacting just with Ethereum, get all your money back. Okay. And with parachains, you obviously can do it. If they stop the parachain, or like sidechain, what you call it, then your money is gone. And with L2s, you are still protected by Ethereum, and if everything goes down, you can still, just by interacting with Ethereum, get the money out. Okay, so I think that's the most important one.
Okay, so thank you, Antoni, for your presentation.
So also for more interested people, there is an extra slide that you can find under this link, and also it is to my social media. So thanks everyone once again.
Okay, thank you, Antoni, for insightful presentation. And right now, we'll do a 10-minute break because pizza has come and we want it to be hot. We'll back here for the last presentation in 10 minutes. So feel free to grab a slice of pizza, get yourself a new beer, and we'll see each other in 10 minutes.
Będziemy zaczynać z powrotem, także zapraszam wszystkich. Będziemy kontynuować, także zapraszam wszystkich z powrotem już. Well, going to start again, so please appreciate it if you start getting your seats. Okay, so we can start again. Welcome back. Right now we'll have last presentation, which will be which will be presented by me. Sorry, it's hard to it's really hard to announce myself. So I will just start the presentation and announce myself at the beginning of the presentation. So yeah, hi, I'm Max. I'm software engineer of Software Mention, and I'm also doing my master's in Utrecht University in Netherlands. And my research interests are mostly related to programming languages theory. And here in Software Mention, I work on Starknet team, and mostly working on Cairo developer tools. And today, I would like to talk about the topic, which is a bit of in the intersection of those two. And it's a really important problem in a blockchain ecosystem, which is how to not lose money. But it won't be today about any investment strategies. Sorry if somebody expected that. Today, we'll talk about a fundamental problem or feature, depends how you look at it, of the blockchains. So yeah, first we'll start with smart contracts. What is smart contract? How many of you heard this term? As expected, many. So smart contract is some code. We write some code, some application, and we can put it on the blockchain. And it's all we have to understand. And those smart contracts can expose some functionalities to users. And for example, can hold some assets. So for example, we have smart contracts, a contract which holds some tokens, and users from outside world can request it to transfer those assets to other user of the blockchain. And what are the consequences of that? Consequences are smart contracts can hold critical assets. Here is some code of Ethereum wallet. It's just not important to understand. I just wanted to show you that if I do something like this, right now it's highly vulnerable. So basically here, we not validate the sender of the money properly, and anybody can steal your money, which is not the best scenario. So somebody can say, okay, everybody, like for traditional web, developers can as well make some mistakes and write bad code. The case is if I write some code, for example, which handles bank, and it's incorrect. So for example, I don't know, I can send money I don't have. When somebody uses that, bank can revert it in some way. So maybe it will require some fuss, so additional phone calls, but at the end of the day, they can revert this and undo the damage. It is not the case on blockchains, because by design, those are not revertible. So every mistake of a developer is like exponentially extrapolated, which is kind of big deal, and we have to put extra care to make things right. So what we want to do, we don't want to cry and, I don't know, moan all day. We just want to look for possible solutions. First, we can try to read our code carefully. Of course, we don't have to do it ourselves. We can assign other people to do this perfectly. Those people are experts. And we basically call those audits. And if you give it this fancy name, everything is great. But it's basically still conveyed by humans. And there are many problems which can be related to that. Like they can just miss the mistakes like as we did. So it's cool to do that. I'm not saying it's bad. It's just we want to look on better stuff. Next, we can do testing. Testing is a kind of classic approach. So assume we have, for example, maybe consider arbitrary problem of sorting an array. Like we have some numbers and you want to sort them. So when we would like to check it on like doing testing, we just select one specific array and would execute it on our code, using our code. And at the end, we will just assert if the array is in sorted state. So it's as expected state. It's cool. It generally it's how we do it in Web 2. And it gives decent guarantees. But we can do better. Yes, we can do better. We can look in something like fuzz testing. So instead of providing the expected answer, we can write code which validates an answer. So we have if still considering array sorting algorithm, we write a code which checks if array is sorted. This way, when fast testing our code, we can generate big number of arrays and put each of them through our code, and at the end, check each of them if it's sorted at the end. So this, we can see, can provide much stronger guarantees than traditional testing, but still there can still become some misses, because for many cases, this number of possible inputs to the code can be infinite or at least very big. And it's infeasible to just test it each time or even once. And at the end of the spectrum, have formal verification, which is the holy grail here, because we could just assume input is any array and automatically, mathematically prove that output on our code which will be always a sorted array. Which sounds very cool, but there are some problems, and I would like to get into first how it's done. Okay, so it isn't something I'm just taking from a hat. It's something that's actually adopted. And for example, Solidity, if you are familiar at least a little bit with Ethereum stack, on Solidity, if you download Solidity on your computer, it includes some kind of formal verification you can execute. And I know there's maybe a bit too much code to read. Sorry for that, but I just wanted to show it, to give you a feeling of a real-world example. So here we have some function which takes an array and finds a maximum element from this array. So at the top of the function, we can see the code which calculates this element and sets m to it. And at the end, we provide something which we call formal specification. What formal specification is? It's the way we define correctness of our code. because it would be unreasonable to assume our computer will know what code being correct means. Okay, so here, what we do, we just iterate over the array and provide an assert. For each element of the array, we check if our maximum element is greater or equal than the element of the array. So we can assume it defines how maximum element, what maximum element of an array is. Okay. How right now we can take this formal specification and show with it like our code is correct, this code above. So we will get into a bit simpler example here. So we would like to look into a function which looks like this. It's very simple, just like for a purpose of demonstration. So here we have a function that takes one variable. It defines y variable, which is assigned to x. Defines z variable, which is assigned to some random value. And at the end, it increments x by 2. And our formal specification here is like x is greater than y. If somebody is good at looking at such stuff, he sees right now it's correct. Like it always happens, so this specification always be satisfied. But how to do it automatically? So computer can do it, not our poor, tired eyes. So okay, what we want to do is symbolic execution, which is a weird term, but what we want to do, we want to, instead of executing code on some values, we want to take our specification as a value and execute it backwards. So what does it mean? For this example, our formal specification was x is greater than y, so we start with value x is greater than y. And then we go upwards. So first, we can see like x is assigned to x plus 2, and we executed this assignment on our specification, and right now our specification is transformed to x plus 2 is greater than y. Sorry. And then we executed on one instruction upwards, and z is not included there, so it basically has no effect on it. And at the end, y is assigned to x, so we basically, what we do is replace y with x. And this is the final result. Does it make sense? Anybody has any questions here? Yeah.
You still have to include this x is bigger than y on the bottom, right?
Yeah, it has to be specified by developer. Yeah, because like you have to define in some way what is correct, because computer cannot know. Like you can write some, you might have as a developer any expectation about the code, but that's true. Any more questions here?
So you always like have to go to some kind of a tautology to make a formal verification.
Can you repeat the question? Sorry.
So you have always like to go through some sort of tautology to have a formal verification, because if you haven't like y equals x here, you wouldn't have like any reasons to believe that that code is correct.
We'll get in 1 second to that.
Okay.
It's just like right now, just how we reduce that, it just makes sense. So here we can see like our code is correct if this equation holds for any value of x.
What if x overflows?
Okay, this is an important question. And here, for the sake of example, we don't consider that. We just consider always uints are correct uints. You probably would like to include your formal specification at the end. Yeah, like it's complicated to do that, like to explain for everything and consider everything, but that's true. And I think like if you go into official Ethereum docs, formal specification will include like some examples of overflowing, because you can verify those as well. So does that make sense? If like for any value of x, this will be satisfied, our code is correct. According to our formal specification, we defined ourselves. Great. Of course, like as Pavel mentioned before, if, for example, because if we look on this example, it's pretty obvious that it's always correct. Because if we increment x by 2, it will be always bigger than itself. But for example, if it would be y on the other side, it wouldn't be always true. So here, what we want to do is we would like to do it automatically, because those examples can sometimes be much more complicated and much bigger. So we cannot see it with our eyes. So there is one problem in mathematics and computer science, which is called satisfiability module of theories, which answers a bit similar question. We just find a value which satisfies a set of inequalities. Or just it's like in generality, but in specific case, you just check if there is any value that satisfies inequality. So we want to use that. And tools that do that are called SMT, satisfiability module of theory solvers. And there is lots of advancement in such tooling. For example, one of, and probably the most popular of them is from Microsoft. It's named Z3, and it's mostly built for formal verification purposes. And what SMT solver does, it takes a set of inequalities, which can be a bit more complicated because those can also include some logical formula stuff. But generally, it takes sets of inequalities and returns a value that satisfies any value. But we wanted to show that this is true for any value, not check if there any value that holds it, because it will be a bit similar to testing. Just look for one value that our code works, but we don't check if it works for all values. It's useless for us. So what we want to do right now is some small logic trick. We want to negate our value for our equations. So this way, we make our SMT solver to look for a counterexample for our code. And we hope it to fail, because if it fails, we pass the test, our code works. Does it make sense? Great. So it's perfect world. We don't have any more bugs, yeah? Why we started using it tomorrow? World is not perfect, yeah? We have problems here. So first, and the biggest one, if you do any kind of course on formal verification on university, first thing you learn is a lost battle, because we cannot do that for every code. It's proven mathematically, because that we cannot show, we cannot write a code that verifies if other code will always end. So we cannot generally verify our code. But there are some tricks we can do to provide very strong guarantees, which will be sufficient. But also for blockchains, we always also consider finite executions, because we have a concept of a gas. So generally, it plays nicely with the concept of blockchain, which is good. That's why I want to use it there. Next problem is SMT solving is NP hard. It's very hard word to saying. It's very complex to calculate, and we don't have good algorithms to do that. We have some approaches, and there is lots of work done in computer science in recent 20 years to make it as fast as possible. But generally, it's still unfeasible for very large code bases. The thing is, for blockchains, those code bases aren't that big. We write approach for blockchain, we generate smaller modular smart contracts which interact with each other. So generally, it's much easier to do so than, for example, some random Java code base which you can encounter somewhere else. So it's good. It also plays nicely with our approach and our problems. And the problem number 3, which was mentioned before, and also I think mentioned it briefly, we need to write those requirements, which is generally harder than programming itself. Because I think I showed you before an example of formal specification of looking for a maximum value. So this specification we provide is kind of flaky, because it doesn't check if the element which M is set to comes from the original array. So it could accept incorrect code. So And what we see here, it's a kind of problem, but still, it can provide some guarantees. So as a summary of this talk, and what the feeling about the formal verification I want to leave it with you, I want to leave in you, is like, it's another tool which can help you mitigate the risk. And it's already adopted. Many projects which develop smart contract on blockchain use that. And you don't want to treat it as a holy grail that solves our problems. But we actually can use that, and it's usable. And it can provide you many additional guarantees about your code, which is great. And I think generally in security, we just want to mitigate the risk because real world is so complicated that we cannot solve everything and have no problems I have no problems at all. Okay, that's it from me. If somebody has any questions, right now, it's a great time.
Okay, so when you talk about SMTs, they are really just like bounded to the inequalities, or does it cover like a set of logical operators, like and and ors?
So basically, I don't think I need that, but I can show that. Okay, never mind. Yeah, it's basically SMT. If somebody is familiar with some concepts from theoretical computer science, SMT is generalization of SAT. Yeah. So basically, it extends classical like SAT with some inequalities. So it's stronger guarantee.
Okay, so yeah. So you could like just do a reduction from like just all logical operators to only inequalities. So you could like prove that SMT is also NP-hard from the SAT.
Yeah, that's how we can prove it. Like it's the easiest way. Yeah.
Hi. Hello, hello. Thanks. I would like only to mention about another strategy of maybe it could be a solution to or to prevent which can be make something wrong in code of smart contract. I don't know if you're familiar with multi-signature wallets, when you can take another person to can say if this transaction is okay or not. So if something is wrong in this transaction, you can take another person. If you take a multi-signature, or maybe you can make an extra clause or extra provision to take this dispute about this problem of executing, of doing of something in this smart contract. You can take it to another person, like institution. For example, Kleros. It is it is a decentralized application which is made to dispute resolutions. Yeah. It is some kind of alternative dispute resolutions in decentralized world. Thanks.
Yeah, that's true. That there are many different, like because I mentioned, it's a big problem and a feature because it's hard to call it a problem of smart contracts because like if we wanted to do that, it's like what we wanted exactly. We don't want it to be reverted by anybody, at least by like some random entity. But on the other hand, it's a big problem, and there are many solutions to that. Like I think, like even like formal verification has many more flavors itself. I think, like I mentioned, like the most popular one and most like I know from my perspective a bit maybe interesting for general audience. But there are lots of stuff we can be done there, and those can include like, as you mentioned, a bit more like human-based auditing, and as well as like using computer to help us.
Hello.
Hi.
Thank you. I've got a question about formal verification of that complex stuff, for example, as consensus of Ethereum 2.0. They someone, third-party service, provide them formal verification, but it's blow my mind how it's possible to verify so complex stuff as like that. Maybe you can explain into words how it's working.
But can you repeat your question? Sorry, because I'm not sure.
Yeah. I'm trying to understand how we can use formal verification for something more complex than that function. And as example, we can select, I don't know, a lot of things from Cardano or Ethereum consensus or any other stuff. Maybe you can explain in 2 words how it's working.
Okay, generally I think, as I mentioned, defining formal verification is often hard, like defining those guarantees. We can never expect it to be 100% correct because people develop those requirements. But generally, I'm not sure if I do exactly with a process how to do it because it's just like how writing code does. Like a bit on the other side because instead of writing code, you write some like formal specification. And like in general, like it's something you do in your head when you write code, yeah? Because if you want to write code, you have to imagine how it wants you to act in specific scenarios. And then you have to provide constraints how you want to work. So I think the approach is like general approach to doing such complex things and like mathematics and programming, and I think most people use that. It's just like, okay, it's have adversary thinking. So you define some contract, and then you provide some, okay, I want it to only, to always, I don't know, to value of, for example, the number of tokens always be greater than 0. And then you come up with adversary. Adversary is an entity which can, like, you imagine to being like attacking your contract. And you design an attack, and then you update your formal specification to protect it. And then you go back again, adversary, attack, update, like the cycle. And it's how you do it. Like it's a process.
So if I just could add on that, I think like formal verification could be applied to larger contracts and more complex contracts, like in a manner of divide and conquer. So you take smaller problems that you have, like basic principles of your system, and try to break them, like Max said. And I think if you come up with a sufficient number of those principles, I think you will come up with a system that is able to protect your system pretty well from those flaws that might happen.
But how you can understand it's pretty well and here not so pretty well? Where you can what's the difference behind, in that case, what's the difference behind testing and formal verification? Because I can't see the difference.
I see your point. Like generally, it always ends up on humans can make mistakes. So generally, okay, I can give you some examples here. If you divide, for example, if you devise formal specification, then if you modify the code, you can still check if it holds. Yeah, so basically it's still like the game is the same as testing, but after, like for tests, if you want to write a test, you still have to devise the property. Here you just have more expressive language to do so. I think it's it. And if you like use this more expressive language, you can show it like for all of them, at least for majority. Like this is the problem of halting it. But that's I think getting into the weeds. But yeah, that's true. Like that's the problem here. Like we still have to write those requirements, and this can be bad. But I think it's better, it's easier to get into this game of adversary. And for example, it's sometimes a bit easier to have people who define them separately. It's also useful for testing as well. But here, I don't know. Like you can, if somebody else defines the constraints, the formal requirements, and somebody else is writing the code, it also can help because you can mitigate some stuff. But as I said, it's a game of still human errors can encounter. We can have a silver bullet here.
So my question is from the developer experience perspective. So let's assume that I know the formal verification and I know that I would like my program to be formally verified. So should I, from the beginning of the writing, just think about that it will be at some point formally verified? So probably more of a functional program, or or can I just, write my flaky code, my flaky object-oriented code, and later it will just be formally verified?
I think I would approach it. I would try to define the specification, and then I write tests as well this way. I just write tests and write code. But
so it means that when I'm writing the tests, I'm also writing those specifications.
Yeah, I think tests. Okay, maybe to give you some context, if you have a formal specification, you can use it to automatically generate tests. So unit tests at the beginning. So, or you can also, for example, if you have this, if I go to this formula, so those are very closely related. It's just here you write your requirements in more general way. Because, for example, if you have this equation, if you test it on random values, it would be equivalent to fast testing. So, and I read recently a paper which tries to create a SMT solver on GPU, which runs into thousands of threads and speeds up some stuff, but provides less strong guarantees. Yeah.
So, for example, if I have my code base and I submit into the formal verification, it means that the verifier will just try to come up with these requirements, right? And create those inequalities to check?
Yeah, you have to write those asserts, looking for the solidity, you have to write those asserts, and those equalities will be a result of the symbolic execution, because your formal verifier can do that.
But isn't it still relying on that people will just come up with the good requirements?
Yes, I said that. That's true. Some people consider that simpler, and you can find a lot of mistakes this way. It can be proven. I think it's like I said, there are different flavors of formal verification. But for example, you have methods to prove protocols. For example, you also have to internet protocols, those are deadlock free, and you have to do the same for blockchains. And generally, those are kind of very well proven and good to finding small mistakes. For example, for hardware, it's heavy. If you look into careers on Apple or any company that does some hardware, they basically have always have some formal verification people, because there it's heavily used, because they can do lots of small mistakes there, and it's similar in blockchains.
So basically, from the developer experience, I think still, if you know that your code will be formally verified, you still need to think about it and to have those requirements, because if you just write the flaky code and assume that the verifier will just come up with the good assertions, it's basically as the audit, right?
Yeah, that's true. But if you if you have it's, of course, it's it still collapses to this classic I have to have this nice example. It still collapses to it. People can make mistakes. It's just a method which can you expand on that and give people stronger tools to work with them. And this is the case, because many people find if you maybe even of the level of the mind game, it's easier to look, how to define is correct. Might be easier than just looking at the code, it's correct or not, yeah. And also audits, if you have audits, I think they're using some formal constraints as well. They have some specification they want to check for, and some often formal stuff. So basically, it always collapses to that. You write software, you also often first try to gather our requirements, and then you write the code.
Okay, thanks.
Any more questions? Oh, there was one question there.
So I have one question about how those solvers compute those results or verifies this statement. You mentioned about that they're using GPUs and threads on it to...
No, just classical approach, I don't think it's GPU based, but I'm not expert on SMT server itself, so I just...
Is this some kind of simple brute force approach to check every possible solution, or is there some algorithm behind it that simplifies this?
Yeah, generally, there is no algorithm which works in general. So because it's NP hard. So I think if we had an algorithm for that, we could have much better things that like making our blockchain code secure. But there are some classes of such problems which often like occur in your world, which we can often simplify or make them faster. Yeah, so basically it's often based on heuristics and developing them properly so you can reduce some problems, make them simpler.
Okay, thank you.
Any more questions? Great, okay, there's one more.
Yeah, so my question is like, is the theory behind this proving assumes that the code is being executed on one core in a single thread? How would that solver?
Okay, for example, I show you. Yes, it assumes that. But there are like, it's one of the techniques. For example, there are something like called temporal verification. Like if you heard the term TLA plus, maybe I have somebody on the analyst also heard that, which is used more for like multi-core stuff. And it's, for example, it has been used for verifying some network protocols that those are, for example, deadlock-free. It's a bit different, and it works more on automata theory. But generally, what it's there, you have like specific logic language, which is like kind of model language, model logic, and this logic includes some operators, which are like always or at some time, and you can write your properties there. So, for example, you can, I don't know, if you have some multi-threading problem, like 4 or 5 philosophers problem, you can model this problem, like your algorithm in this tool, and then write this formal specification. And for example, you can devise a formal specification that is like it's deadlock-free. And it actually is very good. Like if you play around with it, you can see like it's much easier to come up with specification that something is deadlock-free than to write a code that is deadlock-free. And those are also very heavily used for like networking and stuff like that. Okay. I think like last question, or we can wrap up today talks. Okay, great. Thank you all then. At the end, I have some announcements. So first, it's the first meetup, but not last. We'll be holding next sessions, and you are doing something interesting, and it doesn't have to be strictly like technical. I think like if you have something interesting to show, feel free to reach us on Telegram or Twitter, and just like find our website and write an email. And we are welcome any talks in the future. So feel free to do that, and we'll much appreciate that if you do so, because it's always great to have other people tell what they're working on. And a bit unrelated to blockchains is if you want to take a photo, sorry, because I see you take a photo. If somebody wants to take a photo of that, you can do it right now. I think we generally accept, like not everything. I cannot promise you I accept everything, but if it will like, I think those talks today give you a general vibe what we are looking for, but you also would be happy to maybe expand it a little bit. So I think if you have an idea, just reach to us. Maybe we can either try to either say it's great, or maybe you can direct a little bit. Maybe this way we'll be fitting a bit more. But I think like I would say we are open for everything, and if you want to talk about something, feel free. Okay. And it's unrelated, but if somebody is into multimedia and on our streaming related stuff, we are doing a conference on multimedia streaming, because it's like other specialization of software mention. We are doing lots of stuff related to streaming. And if somebody is into that, as I said, feel free to join the conference. It will be in October this year. Okay, great, thank you then. We'll be there here from some time, and probably like it's our network if somebody wants to talk about anything. feel free to take fresh beer and enjoy your time. And thank you once again for attending talks, and see you in the future. Probably this next meetup, we aim for early autumn or something like September, October, I think, approximately. Okay, thank you.